In this lesson, I'll show you how to find the complete solution of a second-order differential equation. This is question number 2. The question reads, solve y double prime minus y prime minus 6y is equal to 36x plus 50x. Notice that the right side of this differential equation does not equal to 0. And if it did equal to 0, this part specifically, then we wouldn't be following the steps that I'll be showing you next. To make things easier for us, I've written down all of the steps that you need to get the complete solution. The first step is to find the complementary function y sub c by solving the auxiliary equation. Now take a look. Every complete solution of a second-order differential equation with the right side not equaling to 0 looks like this, where we have y is equal to a complementary function plus the particular integral. We're starting with y subscript c. Now to find the complementary function y subscript c, we need to focus on the left side. Notice that the left side has all the y terms. We have y double prime, y prime, and 6y. What we have to do is rewrite this as if it were a quadratic. So using the letter m, I'll write this term as m to the power of 2, this term as minus m, and this term as minus 6, and I'll make that equal to 0. Next, I'll factor this. I need to find two numbers that multiply to negative 6 and add to negative 1. Those two numbers are negative 3 and positive 2. So I'll write down m minus 3 and m plus 2. If I solve for m, I end up with m subscript 1 is equal to positive 3 and m subscript 2 is equal to negative 2. Using these two very important numbers, I can write down the complementary function. So I have y subscript c is equal to c subscript 1, my first constant, times e to the power of my first m times x, plus c subscript 2 times e to the power of my second m, which is negative 2x. We've just completed step number 1. Let's move on to step number 2. We have to write the particular integral y subscript p in this step. It should contain each term from the right side, f at x, as well as the first and higher derivatives of each term of f at x. Here's what I mean by that. Take a look at the right side of this equation. We have two terms. For each of those terms, we need to find the first and second derivative. Let's start with 36x. We have f at x is equal to 36x. The first derivative is 36, and the second derivative is equal to 0. Since we've reached 0, we stop. Let's try the next term. It was 50 sine x. So we have f at x is equal to 50 sine x. Taking its first derivative, we get 50 times cosine x. And its second derivative is negative 50 times sine x. The terms we will use to model our particular integral yp will be 36x, 36, 50 sine x, and 50 cosine x, less their coefficients. We don't regard the 0 or the repeated or duplicated trigonometric functions. And just to be extra clear, by duplicates I mean terms that are alike regardless of their numerical coefficients. Step number 2 is done. Let's move on to step number 3. Step number 3 says, if a term in y subscript p is a duplicate, alike, of 1 in y subscript c, multiply that term in yp by x to the power of n, using the lowest n that eliminates that duplication and any new duplications with other terms in yp. Comparing the terms from yc and these possible terms that will form y subscript p, we see that no term in y subscript p is a duplicate or alike in one in y subscript c. Take a look. This is y subscript c, and these are the values for y subscript p. Step number 3 is done. Let's move on to step number 4. Now we have to write yp. Our particular integral yp will look like this. We have yp is equal to a plus bx, where this term represents 36, and this term was generated because of that 36x, plus c sine x, representing this, plus d cosine x, representing this. Step number 4 is done. Moving on to step 5. We have to substitute y subscript p and its first and second derivatives into the differential equation. So let's find y prime p is equal to, this goes away, this becomes b, I'm using the power rule here, this becomes c times cosine x, and the derivative of d cosine x is negative d sine x. Remember that the derivative of cosine x is negative sine x. Finally, our second derivative, we have this goes to 0, it's a constant. This becomes a negative c sine x, and this becomes negative d cosine x. Now I need to substitute all three of these into my differential equation. Remember that our differential equation looked like this. We had y double prime minus y prime minus 6y was equal to. So in place of this, I'll write down y double prime p. In place of this, I'll write down y prime p. And in place of that, 6 times y subscript p. The right side stays the way it is. Next is the repetitive part. I have to substitute these two terms into here, cosine x. Substitute these three terms into here, and notice that there's a negative, so this will become negative, this will become negative, and this will become positive. And finally, multiply each of these terms by negative 6. So we get negative 6a, negative 6bx, negative 6c sine x, and lastly, negative 6d cosine x is equal to the right side. 36x plus 50 sine x. This completes step number 5. In step number 6, we're asked to evaluate the coefficients by the method of undetermined coefficients. So what we have to do is collect like terms. This term and this term is alike. So is this. So is that. This term, and this term are alike. The x terms are alike. So this one and this one. And the constants are alike. Negative 6a and minus b. Let's start with the easiest, the purples. We have negative 6bx is equal to 36x. We don't have to worry about the x's. They'll cancel out. And this leaves us with b is equal to 36 divided by negative 6, and we end up with our b value of negative 6. Next, let's move on to the ones that are highlighted in green. We have negative b minus 6a is equal to 0. We can replace this negative 6 into there, which makes it positive 6, and bring this term over, which makes it positive 6a. Therefore, a is equal to 1. We found b, we found a, now we need to find c. For that, we'll relate these four terms, starting with negative c sine x plus d sine x minus 6c sine x is equal to 50 sine x. Notice that there's a sine x in each of these terms, so we can disregard those, leaving us only with our letters. Minus c plus d minus 6c is equal to 50. Notice that I can't find c or d yet. I need to generate one more equation. And for that, I'll relate the terms that are in this color. We have negative d cosine x minus c cosine x minus 6d cosine x, and that is equal to 0 because there are no like terms on the right side. The cosines can cancel out because they can divide out, leaving us with negative d minus c minus 6d is equal to, combining the d terms, we end up with a negative 7d minus c. We can solve these two equations simultaneously because they look like a linear system. I can take the c over, that gives me negative 7d is equal to c. And then I can replace this into my c and here. This gives me negative times negative 7d plus d minus 6 times negative 7d is equal to 50. We have 7d plus d plus 42. D gives us 50. These are all like terms, and that means d is equal to 1, because this adds to 50, dividing both sides by 50 gives us 1, and we can substitute this into here now, where we have c is equal to -7. I'm going to highlight the key numbers that we found. We found d, c, a, and b. In our last step, we have to combine yc and yp to obtain the complete solution. The complete solution, therefore, is y is equal to c1 times e to the power of 3x plus c2 e to the power of -2x plus 1, the value for a, minus 6x, -6 being the value of b, minus 7 sine x plus cosine x. Remember, there's a 1 right there. And there you have it. That is how to find the complete solution of a second-order differential equation where the right side is not equal to 0.